final portion for this chapter is ionization energies. So the first part that you need to learn is that you must know how to write the equations for first ionization energy, second, third, fifth, and n. What you can see down here is that the definition is such that if you're looking at the first IE, then you'll be talking about producing a cation with a charge of +1 from actually the element, and it's important to note that both are in gaseous state. In the exam, if you do not label the gaseous state symbol, then you have marks deducted off. So if you look at the fifth IE, then we are talking about producing a cation with a charge of 5+, because 1 mole of electrons is going to be removed to produce 1 mole of X5+. Hence, you must start off with 1 mole of X4+. Next, we'll now look at the factors that will affect ionization energy. It is building on what you have learned on the factors that affect the size of an atom. Because if you want your ionization energy to be high, then you will want your nuclear charge to be high, because you want a very strong attraction force. You want your shielding or screening effect to be low, so that it doesn't push the electron out that easily. But one key factor is actually the atomic size. This is the additional factor that in ionization energy you have to factor in. Because the further away the electron is away from the nucleus, then you will expect the ionization energy to be lower, because it's easier for the electrons to be removed. Let us take a look at the first ionization energy and how it changes when you move down the group. So you can see evidently, based on the 2 graphs that's here, the first IE decreases down the group. The reason is because as you go down the group, you know that your shielding effect will start to increase, as earlier explained in the earlier section, as you have more fully filled electron shell. Your nuclear charge will increase as you have more protons. And the more important point, or the additional point to consider, is that now the outermost electron will be further and further away from the nucleus, because the size of the atom increases down the group. So the way to present that is that increase in shielding effect coupled with a larger atomic size outweigh the increase in nuclear charge. So that result in a decrease in the effective nuclear charge. Electrostatic attraction force on the outermost electron decreases down the group, the first IE decreases. It is also good at this stage that to remind that if you forget the size of the atom, all right, that the size of the atom decreases down the group, you can always take a look at the data booklet. You can see down here, we have it lined in terms of the period. So you can see as you go down across the period, the size decreases, all right? If you go down the group, the size increases. However, there's another argument that's more prevalently being used in prelim exam or when you go to J2, all right? So you find that if the same question is being asked, why the first IE will decreases down the group, one could very well argue first by listing the electronic configuration and then mentioning that, well, if I want to remove an electron from 2s, in the case of lithium, or 3s, obviously your 3s subshell is of a higher energy level. If your 3s is of a higher energy level, you will therefore require less energy for it to be removed, all right, as compared to your electrons inside the 2s, which is of a lower energy level. So the way to present the argument is just simply to say that the less energy is required to remove electron from the 3s subshell relative to 2s, since the 2s subshell is actually at a lower energy level. With that, let's take a look at the first ionization energy of the elements across the period. Let's take a look at the data booklet. In the data booklet itself, they present all the various ionization energy. So if you want to take up, say, for example, elements in period 2, which is from lithium to neon, you can see that the trend of the first IE actually increases. All right. Then again, from sodium all the way until argon, the ionization increase again as well. So the general trend is that first ionization energies of elements increase across the period. Let's take a look at the reason why. First, shielding effect is generally the same. That is correct because remember in the earlier section, when you look at sodium and all the rest of the elements from the same period up to argon, all the electrons is being added to the outermost electron shell. Therefore, only the first and second electron shells are fully filled, and those are the electron shells, or those are the electrons that provide the shielding effect. So the shielding effect is generally the same. However, the nuclear charge will increase because you have additional proton. And because the atomic size of the elements decreases across the period, that will lead to actually a higher effective nuclear charge. And a higher effective nuclear charge will mean there will be greater electrostatic attraction, and therefore that helps to explain why the first ionization energies of the elements increases across the period. However, there are three anomalies if you observe the trend, and those three anomalies are commonly tested in exam. Let me start off by explaining 2 and 3 first. So earlier, when we talk about show you the trend earlier in the data booklet, we're looking at the trend as such. But in the trend itself, there will always be a slight dip. If you remember in the earlier section, I first mentioned that shielding effect is generally or largely contributed by electrons in the inner electron shell. They are fully filled. Okay? So you will find that the reason why from group 2 to group 13, why there's actually a slight dip that breaks away from the increasing trend, it is because of additional shielding effect as a result of the S subshell being fully filled. Because if you look at electronic configuration for group 13 elements, it ends with XS2, XP1, while element or group 2 element essentially just ends with XS2. So in this case, the fully filled XS2 subshell could provide shielding effect now on your P subshells. All right. So that additional shielding effect helps to explain why there's a general dip in terms of the first IE. The other way to explain it is now to argue based on the energy level of the subshell. If you're trying to remove electron from the subshells, from electrons in XS subshell relative to XP subshell, of course your XP subshell is higher in terms of energy level. If it is of a higher energy level, then it will require less energy for it to be removed. And that also help us to explain why the first IE trend actually has a slight dip or a slight decrease. With that, we take a look at the second anomaly, which is actually illustrated on the graph point 3. In point 3 itself, it occurs from group 15 to 16. By looking at the electronic configuration at the orbital level, you definitely is able to recognize the fact that one of the NPX2 orbital is fully filled now. When you look at the element in group 16, when they are fully filled, you will get additional shielding effect, which means less energy is now required to remove the electrons as a result of the inter-electronic repulsion that occurs between the electron in the fully filled orbital, NPX orbital. Okay? So with this explanation of 2 and 3 in the trend, we'll finally explain the first anomaly as to why there's a very big significant decrease. That decrease helps us to define elements between different periods. As you can see in this line down here, it is from period 1 to 2, and this is from period 2 to 3. Okay? So let us take a look at the reasons and the explanation. So let's consider neon and sodium. Okay, neon is actually in period 2, while sodium in period 3. Why there's actually a very significant drop, which is actually specifically this line here. First, by looking at the shielding effect and by looking at the electronic configuration, it is quite clear that sodium has basically another one more fully filled electron shell that provides shielding effect. Okay, while if you were to compare the nuclear charge, sodium relative to potassium merely has 1 additional protons. So bear in mind that it has 8 more electrons now that contributes to shielding, but it only has 1 more additional proton. And certainly sodium is much bigger in terms of atomic radius relative to neon. So all these factors point towards the fact that the increase in the shielding effect is very significant, while the increase in nuclear charge is just moderate. Okay, as highlighted here. And certainly bear in mind that there's also a significant increase in terms of the atomic size as well. So hence, the effective nuclear charge decreases, and that leads to a significantly lower first ionization energy. With that, coming to the last portion. The last portion is to look at the trend of successive ionization energy of the same element. Those information are also presented in the data booklet. As you can see, you can take neon and you can look at the ionization energy that's been given. All right, successive ionization energy from the same element. So the examples and the graph that we plotted here is none other than your potassium. All right, we are plotting log ionization versus the order at which the number of electrons that's been removed. All right, as you move from the first IE towards maybe the 10 IE, the 10 IE will have significantly larger value. All right, so logarithm will give better representations on how the value increases from a graphical perspective. So quite clearly from here, we notice there's actually one thing. All right, there's actually one trend. The trend is that there's obviously an increase, okay, in the ionization energy as more and more electrons are being removed. The reason is because as more and more electrons are being removed, you will increasingly have more protons than electrons. Having more protons than electrons means that you have higher effective nuclear charge. A higher effective nuclear charge will naturally means that there's stronger electrostatic attraction force, therefore giving rise to an increasing trend of ionization energy. However, we notice there's actually jump when a certain number of electrons are being removed. You get a significant increase, all right, in terms of the log IE. The reason for that is when electrons are being removed, all right, because now you are removing electrons from the inner electron shell. So let's take a look at the electronic configuration. So the first thing you have to bear in mind, when they start removing this electron, they are actually removing electron from the 4s subshell. When you remove electron from the 4s subshells, the one that's providing the shielding effect is actually the electrons inside the first 3 electron shell. So therefore, we expect the ionization energy to be low. But that is no longer true when you now remove the second electron. If you now remove the second electron, you are removing now electrons from the 3p subshell. In this case, the shielding effect dramatically decreased because now the shielding effect is only provided by electrons that are inside the first and the second electron shell. Hence, because of this, you will get a significant jump. Now let's take a look at the significant increase when you remove the 9th and the 10th electron. When you're removing the 9th electron, you are in actual fact removing electrons from this subshell. All right? It is the last electron. It is the final electron inside your 3s subshell. But when you remove this electron, you will now be removing electron from the 2p subshell. And you can see the reason why. The very moment you remove electron from the 2p subshell, again, the shielding effect significantly drops because only electrons in the first electron shell now provide the shielding. Finally, let's take a look at the final portion where there's again a significant increase. The 17th electron that you're removing is actually removing electron from the 2s subshell. However, when you remove the electrons, the 18th electron, This electron is actually from the 1s subshell, and generally if you remove electron from the 1s, there's a zero shielding effect now. Unlike when you remove electron from the 2s, you still get shielding effect from the fully filled 1s subshell.